So how do solutions form? Let's look at sodium chloride dissolving in water. So sodium chloride is held together by attractions between the cations and the anions. We call those ionic bonds. And now we've talked about the types of interactions that occur between water molecules, and those are hydrogen bonds, as well as the dipole-dipole forces and the dispersion forces. In order for sodium chloride to dissolve in water, we have to replace the solute-solute attractions that we're going to break, and the solvent-solvent attractions that we're going to break. Those need to be replaced with solvent-solute attractions. We can't just break these forces of attraction and not replace them with something. That's not going to work out. So things like sodium chloride are soluble in water. Many ionic compounds are, but we know from our study of the solubility rules that not all of them are. Not all ionic compounds are soluble in water. An example is calcium carbonate. The attractions between the calcium ions and the carbonate ions are too strong, and it just doesn't dissolve in water. And we looked at the solubility product constants, and we saw that some of these, they'll dissolve a little tiny bit, but not very much. And exactly why that is way beyond the scope of this class, so we're just going to ignore it. But let's look at how soluble ionic compounds dissolve. So here we've got an illustration of sodium chloride. And it's just sodium chloride, sodium chloride, sodium chloride, and it just goes on and on like that. And these are held together by ionic bonds. And out here we have water molecules, and it's not shown here, but the water molecules interact using hydrogen bonds. And so in order to get the chloride ions to come out and swim around in the water, we have to make them feel comfortable. We have to break their interaction with the sodium ions, and we need to replace that with something so that they're not lonely. So what happens is water is polar. It's got a positive end, and that positive end will be attracted to the negative chloride ion. And you'll get a bunch of water molecules that come around. And they're all chatting him up and being really friendly, and hey, come on out and play. Oh, you don't need those guys anymore. Come out with us. And so they'll get around the chloride and they'll lure him out into the water. And then over here, the same thing's happening with the sodium. But the water's polar and it's flipping its other side to the sodium. The water can interact with the positive ions and with the negative ions. And that's why it can dissolve and separate those ions. So it turns its negative end toward the positive ion and replaces the interaction that the cation had with the anion by these smaller but more numerous interactions with the water molecules. And so it solvates the ions and allows them to move around. So when we put sodium chloride and dissolve it in water, the ions separate and they disperse. They move around, they separate, they become a homogeneous solution instead of just sitting in a lump on the bottom. Of course, there's a limit to how much sodium chloride you can dissolve in water. And if you want to, waste some salt, you can go home and try it. I would recommend trying it with a small cup of water because a lot will dissolve. But we can measure how much. And so what we call the solubility of a compound is generally the amount of the compound. Usually we report that in grams. The amount of compound that dissolves in a certain amount of liquid. So typically they'll say how many grams in 100 grams of water. So the solubility for sodium chloride is 36 grams in 100 grams of water. So at that point, when you have 36 grams in 100 grams of water, that's the limit. If you put a little bit more sodium chloride in there, it's not going to dissolve. In order for it to dissolve, each of those ions has to get surrounded by water molecules. The water molecules at 36 grams per 100 grams are all busy escorting these other ions around, and there's none left. It's full. So we say that's a saturated solution. The solution is saturated. It's full. Can't take any more. So a saturated solution means that it has the maximum amount of solute under the solution conditions. And different things can affect the solution conditions. You add more, it's not going to dissolve. I don't know what's up with the pointer there, it went away. Or what if we have less than a saturated solution? My iPad is stuck on the previous slide. I don't know. Okay, there we go. Good. Thanks for joining us. Unsaturated. That means we haven't reached the solubility limit yet. It's holding less than the maximum amount, so if we add some more, it will dissolve. Means you can put more in. And then there's this crazy situation called a supersaturated solution, which is one that holds more than the normal maximum amount of solute. These solutions are unstable, and that extra solute will normally precipitate from the solution. These can be formed under special circumstances. They're formed in a can of soda, where there's a great deal of pressure of carbon dioxide over the solution, and we'll look at that in a minute. They can also be formed when you create a saturated solution at a high temperature and then let it cool down slowly. And that's an example here. So in this beaker, they heated it and dissolved a lot of sodium acetate in the water. And you can see it's nice and clear. It's a homogeneous solution. If you let that sit there undisturbed and cool down, as the temperature falls, the solubility decreases, but it's kind of lulled into a false sense of security. It doesn't recognize maybe that it's saturated, oversaturated. And then if you disturb it, so here they're just poking it, they're just touching it with a glass stirring rod. And then what happens is it kind of wakes up and like, oh, hey, wait a minute. And then all that extra sodium acetate begins to crystallize out of solution. And it's really pretty amazing to watch. So I'm hoping that I'm able to do that demonstration for you on Thursday. It's really cool. And so this is what happens at the end. It looks like it's all solid. It's just that there's so much sodium acetate and so little water that you can actually turn the beaker upside down and nothing comes out. It's really kind of crazy. Solubility rules we talked about earlier. Those give us some qualitative descriptions of the solubility of ionic compounds. And we learned that some things are not soluble, some ionic compounds. And then the book doesn't know this, but we've already done chapter 15. And so we know that there's also quantitative descriptions of the solubility of compounds. And although we say, oh yeah, calcium carbonate is insoluble, that just means that an insignificant amount of it dissolves. We learned from KSP's solubility product constants that almost everything dissolves at least a tiny bit. So ionic compounds may or may not be soluble. Molecular solids can be soluble in water. Table sugar is soluble in water. It's polar, and it interacts just fine with the solvent molecules of water. But nonpolar solids don't dissolve. Lard, vegetable shortening, butter, vegetable oil, those sorts of things do not dissolve in water. So here we have a sodium chloride solution and a sugar solution. Both of these are solids dissolved in water, but there's an important difference. This one contains dissolved ions. There are charged particles. This solution will conduct electricity. This solution contains molecules which are not charged. Sugar water does not conduct electricity. And I should be able to do a demonstration for you of this on Thursday as well. In order for electricity to move through this solution, we have to have charged particles. And so this is called an electrolyte solution. Electrolyte solutions conduct electricity. And this other one is a non-electrolyte. It contains dissolved particles, but it doesn't conduct electricity. And when the Gatorade people tell you that they're replenishing your electrolytes, they are talking about the same sort of thing here. In your body, you need electrolytes, dissolved ionic compounds. There's a lot of electrical activity that occurs in your body, and a lot of other things that require these ions to be there. Sodium ions, chloride ions, potassium ions in particular. So that's what electrolytes are. The solubility of substances varies with temperature. For solids, the solubility usually increases with increasing temperature. So here if we look at, say, lead nitrate, here's the solubility at the freezing point of water. It looks like it's, maybe 37 or so, 37 grams of solute per 100 grams of water. And then as you increase the temperature, the solubility goes up until we get here at, 65 degrees Celsius? The solubility of lead nitrate is 100 grams per 100 grams of water. So as you heat it up, it becomes more soluble. You can get more in. That's the case for most solids, not all of them. The temperature dependence varies. Some of them, like sodium chloride, you can heat the water up. It doesn't change the solubility that much. It changes very little. Other things, like potassium nitrate, it just goes up through the roof. Calcium chloride, you get to this point around 25 degrees, getting close to 30 degrees, and it goes almost straight up. And there are some substances that are less soluble at higher temperatures. But usually if you warm it up, you can put more in. It will dissolve more. This variation of solubility with temperature can be used to purify solids. It's a technique called recrystallization. And what you do is you prepare a saturated solution of the solid you're trying to purify at an elevated temperature. And at the elevated temperature, the saturated solution is going to have more solid per 100 grams of water than it would at a lower temperature. And then you let that solution cool down. As it cools, the solubility decreases, and so you get some of your solid precipitating from solution. You want to let this happen slowly so that the crystal can form, and as it forms, it tends to exclude impurities because it doesn't fit well in the grid. And so they tend to get excluded. If something crystallizes very quickly, a lot of times impurities will get trapped, sometimes even little pockets of solvent molecules and all kinds of junk. But if you do it real slowly, it tends to be much purer. This technique of recrystallization can be used to make rock candy, and that's something you could try at home. You make a saturated sucrose solution, table sugar, at high temperature. It's going to take a lot of sugar. So, small pot of water, and you heat it up, maybe close to boiling, and you add sugar until no more dissolves. And then pour that into a jar and dangle a string in it and just let it sit there. And what will happen is you'll get beautiful big crystals of sugar that grow on the string. And all it is pure sugar.